Okay, even though people did pretty well with transformations on the major quiz, and everybody's class did quite well with that, okay? People know how to transform a parabola. Sometimes people should confuse the horizontal shift with what you do to X. You replace X by X minus the horizontal shift. A lot of people just did replace it by X plus the horizontal shift, essentially. Okay, we'll talk about that in the 161 class. It's everybody here today in that class. So you want to be careful about that. Okay, well, here we have. Okay, well, what has to happen to 2 to the x? What's the difference between the graph of 2 to the x and 2 to the x plus 3? Well, we had some hesitation in answering this, but I did manage to drag out a good answer. Okay, x has been replaced by x plus 3, right? I'm recording it. Okay, so big question here now, and this is where people tended to make mistakes on the major quiz. So for this transformation, x has been replaced by x plus 3, so the horizontal shift is -3. Then we add 2 to the x plus 3. Okay, so it's like y equals 2 to the x, now y equals 2 to the x plus 3, and now y is going to be 2 to the x plus 3 plus 2. It's clear that y has increased by 2, right? Okay. So here's what happens. So what has to happen to each point? It has to shift 3 units to the left and then 2 units up. So, well, I didn't really leave myself room to, maybe I did. Okay, if I go all the way over to the edge of the board, I can actually shift this point 3 units to the left. And let me do that. Okay, so shift from each point 3 units to the left. I'm doing a very good job of making the blinds. We're going to get the idea. Okay. So right here is the graph of 2 to the x plus 3. Now the points are at the ends of these arrows. And of course, we know how to do this. Everybody, you know, I was really pretty well pleased, even though people screwed up the horizontal shift, at the way people did on the major quiz with the parabola. Okay, people understood very well, except getting the horizontal shift backwards in a majority of cases. People did very well with transforming points. So all we have to do is apply that skill to the exponential function, and we're going to be in pretty good shape here. Okay. Now, here then is your graph of y equals 2 to the x plus 3. Now these points have been shifted over here. We don't even have a y-intercept. You have to do an extra calculation to do the y-intercept. Well, you could calculate if you went out to x equals 3, 2 to the third would be 8. Okay, so you'd have a point 3, 8 up here, and you shift it over here, and you'd end up with your y-intercept. Now, at least in some cases, what I just saw was people trying to calculate the y-intercept, and that can be calculated. Okay, 2 to the x plus 3. Well, if x equals 0, y would equal 8, right? Okay, so all you have to do to get the y-intercept there is remember that it happens when x equals 0, you plug x equals 0 in, and there you are. 2 to the third, that's 8. So the y-intercept is 0, 8. What about an x-intercept? Well, there is no x-intercept because the exponential function never touches the x-axis. But the asymptote is still 0. X equal, is still the x-axis, y equals 0. Okay, so we can say that you get a horizontal asymptote. Y equals 0, and that's the x-axis. For the transform for this first transformation, the x-axis is still the asymptote because we're just shifting things over here. That doesn't affect the up or down, so it ain't never going to touch the x-axis, but it's going to get arbitrarily close, just like the exponential function. Okay. The third transformation, or the second transformation, is we add 2. And that's real easy to do. We just lift each point up 2 units. So this point goes up to about here. Got a +2 on that in case you can't read it. Okay, just kind of squeeze in there. And then we do a +2 here. And a +2 here. And then a +2 here, and a +2 here. So we get these points. And this one goes up about here. Okay. And then we sketch on graph. Just using the skills that we developed early before we even talked about the algebraic representation of these different transformations. And we want to think in that context. So there's a graph of x equals 2 to the x plus 3 plus 2. And one other comment, I don't have room to write it. What's the horizontal asymptote? Can you tell me what the horizontal asymptote would be? Okay, now I didn't write it down, but we noted that the horizontal asymptote of this function is still going to be y equals 0 because all these points, they're getting closer and closer without limit to the x-axis, but never touching it, are just shifted to the left, and they still get closer and closer to the x-axis, but never touch it. Now, what happens when we raise all those points up 2 units? Well, since they never reach 0, they're never going to reach 2. Take points that keep approaching y equals 0, and raise them 2 units, they're going to approach y equals 2. So we can make this comment down here. And well, here's our final function. I said a little more verbally with this, so that's worth maybe taking another look at. But they raise the points that approach 0 by 2 units, and now they approach 2. Okay. So the horizontal asymptote is 2. So now we can draw the line where y equals 2. And label this as the horizontal asymptote. Again, that's going to be hard to break. Leave myself enough for it. Made the graph too small. I hadn't originally intended to address all these things. Would have been wiser to use more board space. Okay. But there it is. Okay, so okay, well, those are the important things you want to look at when you transform an exponential function. So now I'm going to kind of show you how we would transform this one. There's a transformation here that you really can't draw along with the basic exponential function. So I might do a simpler one before I do that one. So let's get some board space up here. Okay. Let's take this second function you just about can't see. Okay, well, I really can't demonstrate this with a factor of 1,000. And I want to demonstrate it and then show you how you would indicate what happens by a factor of 1,000. And then people kind of did this on the major quiz, so it shouldn't be a big surprise. Okay, we got h of t. Can't call it h of t. I'm going to call it k of t equals, let's say, just 3 times 2. Well, that's easy. We can kind of look at this and see that on our standard function domain, the biggest number we're going to get is when t equals 2, using the -2, -1, 0, 1, 2 that we use for the exponential function. 2 to the second is 4, and 3 times that is 12. So we're probably going to want our y-axis to go up to 12. Okay. So I'll note three times 10 to the second is 12, so we put 12 on our scale. You might ultimately want more than that, but this is a good start. And then we can do a little subdividing and say, okay, this is about 4 here. So when we graph our basic exponential function, our toolkit function, on the domain that we use in this class, so there's 4, there's going to be 2, there's going to be 1, there's going to be 1/2, there's going to be 1/4. And we get points about here, pretty close to the x-axis. Here, a little higher. Here. Here. And maybe about here. So again, there's our basic function. Okay. Now, we want to vertically shift this graph. If I can find my yellow chalk to follow the same color pattern I did over here. Well, actually, we're doing different transformations. I don't really have to do that. So I'm not going to do that. I'm going to use a different color here. Okay. Okay, well, what's the transformation that we have to do to this function? Is it horizontal shift, vertical shift, horizontal stretch, or horizontal compression? No. Okay, well, I guess I wasn't recording when I explained all this, so we'll just do a synopsis. Okay, when I set my graph up, I noticed that I'm multiplying 2 to the t by 3, so that's going to change the y values in some way. And I think, okay, well, for any basic function, I'm going to graph it from -2 to 2. At least that's where I'm going to start. Okay, well, that means that I'm going to have to go out to a maximum x value of 2 on this graph. I might extend it later, but I got out to maximum x value of 2, or t value in this case. T equals 2. Well, if t equals 2, then I get 3 times 2 to the second. 3 times 2 to the second is real easy to calculate. It's 12. So I have a y-intercept of 12. So I'll not a y-intercept, I have a y value of 12, a maximum y value of 12. So that's why I labeled my y-axis from 0 to 12. Now, and then subdivide this, the 12 into 3 more or less equal pieces. Okay, so I get 4 here, and then 2 is going to be here, 1's going to be here, then 1/2, 1/4, just as usual. So this graph is going to be more compressed than we usually draw it, because we have that multiplier 3. We're going to have numbers all the way up to 12. Okay. Okay, well, these will be the points of the basic exponential function. I don't have to tell you how to graph that. So here are the points of your basic exponential function in blue. Your basic exponential function y is 2 to the t, which I'll write in blue here when I explain what happens. So we asked them, okay, what's the transformation? Well, somebody suggested vertical compression, or a compression, didn't say vertical or horizontal. Okay, but I think you would think of vertical, because we haven't talked a lot about horizontal compression. We are going to talk about it with the exponential function. This will becomes necessary. And since it's necessary, and exponential functions are probably the most important functions we'll talk about in this course for most applications. Well, again, for that reason, this is where we begin to talk about horizontal compressions. There were some open math problems early that dealt with horizontal compression, but nothing on the major quiz or the midterm and deal with horizontal compression. So what I said was, and said it more articulately, because if I go back and explain what I've already done, I've got to remember what I did and what I was thinking when I explained it then, instead of just on ahead and moving forward. Anyhow, here we go. So what we say is that y equals 3 times 2 to the t triples all the values of y equals 2 to the t. I just like when we calculated this. 2 squared is 4, we know that. And we multiply 3 by 2 squared. Well, we just tripled the thing to get to 12. Okay. And among other things, we know that then that our t equals 2.0, which was 2.4, now becomes 2.12. Should be clear why that occurred. So at this point moves all the way up here. Okay. This triples the y value. So the y value is here. We get another one and another one. That my scale is real great. It doesn't really look like a triples, but it does. Okay. Well, you could calculate it, but now you know every one of these y values is going to triple. So here, for x equals 1, well, your y value is 2, and that's going to triple. So we're going to have the y value here, and then we're going to have to add that, or have to add that again. So we'll end up here. Y value is 1. That triples well graphically, and this is what I want you to show when you do these graphs. At least if you do it with reasonable numbers. This is going to triple. So we're going to have 3 of these, and we're going to end up here. And this is going to triple. I'm not even going to draw the arrows, but it's going to triple, so it's going to end up about here. This is going to triple, so it might end up here. Here's our graph. The points that are further away from the y-axis means, so the points that are further away from the x-axis are going to move 3 times as far away because y is going to become 3 times as great. So this is now our graph of three times 2 to the t. Well, if we have the function I gave you 1,000 times 2 to the t, we could do the same thing, but we're not really going to be able to illustrate. Okay, so let's do our h of t equals 1,000 times 2 to the t. Going to turn out we're not, if we do this graph on a scale that shows the function, we're not going to be able to get a sensible graph of the basic exponential function because we're going to have 1,000 up here. And actually, not going to be 1,000. We're going to have to go up to 4,000. So if we graph from -2 to 2, when x equals 2, or t equals 2, 2 to the t is 4, and 1,000 times that is 4,000. So instead of a 12 here, we got to have a 4,000 here. Now the range of the basic exponential function is from 0 to 4, right? So the y values go from 0 to 4. Now where's 4 on this graph? You're going to be able to show me 4? No, if this is 4,000, then 1,000 is maybe here. Okay, 100 is 10 times, just 1/10 of that. 100 is going to be about here. Where's 4 going to be? It's not even going to get out of the line we drew for the x-axis. Okay, so our basic exponential function looks flat. I mean, this point would be 0, 4, but where's 4? It's 1/1000th of this. Okay, so the points of our basic exponential function look like this, and this. They aren't really on the t-axis. But the scale here is so, the Y scale is so big that they look like they're on the T-axis. Okay, so they look really flat at this Y scale, even though they are. So if you can zoom in by a factor of 1,000, you'll see the basic exponential function, but you can't see it at this scale. So what do? Well, we say that, okay, 1,000 times 2 to the T is 4,000. And then we can draw points that correspond to a basic exponential function. We don't really have to calculate them because the basic exponential function has this property that every time you move 1 unit to the right, you double the x value, right? And you have 1/4, then 1/2, then 1, then 2, then 4. So if you move to the left, you have the x value, cut it in half. So we go from the y value, but you move, x moves 1 unit to the left. Y becomes 1/2 as great. So we have y equals 4 here. Half of that is 2. Half of that is 1. Half of that is 1/2. Half of that is 1/4. If you're as familiar as you need to be at this point with the basic exponential function. And on the major quiz, I find that a lot of people weren't. A lot of people still don't totally understand these graphs and where the numbers come from, and we've got to fix that. It doesn't really apply, I think, to anybody in this class, but it did apply to some people in the pre-calculus class. So we gotta fix that. And basically you just have to do what I told you to do at the beginning. So if you're in the pre-calculus class, listen to this. I'm going to recommend that everybody does, because that's exactly what we're going to move into pre-calculus. We're going to take some time today to talk about the major quiz. We need to understand this property of the exponential functions. Okay, so we really need to key in on calculations of the basic exponential function, so we understand its most important property, which is that every time you move a certain distance to the left, you get half as great a result. Okay, every time you move to the right, you get twice as great a result. Okay. Okay, now, again here, we know that when t is 2, 2 to t is going to be 4,000. So that's going to be the maximum value of this transformed function. Now, this function is vertically stretched by a factor of 1,000, just like this one was vertically stretched by a factor of 3. So we can take our point 2, 4 here and move that point 1,000 times as far from the x-axis. 1,000 times this is going to be what? 80 times this is going to be about 80 feet high. Okay, we can't draw it, but we can do it on this scale. Okay, well, enough of that. If we draw this point Then if we move to the left 1 unit, we become half as great. We move to the left another unit, it's half of that, and so forth. So we know that, well, this is going to be 2,000. This is going to be 1,000. And this will be 500, and this will be 250. I'm not going to try to squeeze those in, but we understand that those are the values. Then if you want to go here and plug in t equals 1 and t equals 0, t equals -1 and t equals -2, those are the numbers you're going to get. Again, if you're really familiar with transformations and really familiar with the exponential function, you'll understand everything I just said pretty quickly. If not, we'll think about it. Okay. Anyhow, there's going to be a graph. Oh. Thousand times 250. Now, I had g times 2 to the negative x plus a. I'm going to use unrealistic values in this. We're going to do y equals 3 times 2 to the negative x plus 1. Only got 3 minutes to do this, so I'm just going to lay it out here. And let me see how much more space I've got. Yeah. Let's move a little bit. Okay. So 2 to the x begins by becoming 2 to the negative x. Okay. What does this do? Well, this is a reflection across the y-axis. So that means we're going to take our basic values. Here's the 4 here. No, actually, I'm going to put 12 here because we're multiplying by 3 just like we did over here. So we're ultimately going to need 12, so we're going to put 4 down. And then we're going to put the points of our basic exponential function here, 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 and here. And what are we going to do now? We're going to reflect. So the reflection takes every point here and moves it over here. This point is on the y-axis, so its reflection is itself. And then this point moves to this side. This point moves all the way to here. Then, can't call you by name because the camera's on, but hello, good to have you. I'll move that stuff for you in a minute. Okay. Then what do? We multiply everything by 3. We move everything 3 times as far from the x-axis. So this point's going to move up here and here. It's going to become this. This point is going to move up to about here. This point is going to move up to about here. And then this point will come up about here, and this point will come up about here. So now we have, yeah, that's okay. We have this. And then we raise every 0.1 unit. So our final graph is going to end up. Raise everything in 1 unit. And we end up with a graph, just a little bit. Okay. We end up with a graph. Okay. Now, there are other things we can do with these graphs. If I had a negative 3 times 2 to the x plus 1, what would that do? Well, that would flip this graph upside down and then raise it, flip the purple graph upside down and then raise it by 1. Okay, well, we're actually going to discuss this a little more in the pre-calculus class. And since everybody in the support class is in the pre-calculus class, well, you're going to see most of this second time because I can go through it rather quickly with assumptions that should be valid in a pre-calculus class, but with some comments on things that people might need to upgrade. Okay. So we're just going to kind of continue this discussion, but first we're going to discuss the major quiz. Okay. No, I don't want to say it here. I want to stop that one.